Implementation of autonomous habitat systems for Mars colonization by 2030, a comprehensive report. Introduction. The vision for Mars colonization by 2030 necessitates the establishment of autonomous habitat systems integrating cutting-edge technology and sustainable practices. The implementation plan unfolds in a structured manner involving 4 key phases with a total budget allocation of $150 million. This comprehensive strategy encompasses robotic construction life support systems and communication networks, paving the way for a viable human presence on Mars. Key phases of implementation. 1. Robotic construction. The inaugural phase focuses on harnessing advanced robotics for the construction of habitat structures on Mars. Autonomous machines will be deployed to utilize local Martian materials, significantly minimizing the payload requirements from Earth. Initial estimates for constructing these habitats amount to approximately $513 million. However, this budgetary challenge may prompt the exploration of more cost-effective solutions, emphasizing the need for innovative engineering and efficient resource utilization. Technological innovations. Development of autonomous construction vehicles equipped with 3D printing capabilities. Use of Martian regolith as a primary building material, reducing dependence on Earth-sourced materials. Implementation of modular designs allowing for scalable habitat construction. 2. Life support systems. The second phase is dedicated to the creation of robust life support systems essential for sustaining human life on Mars. Drawing inspiration from terrestrial experiments such as Biosphere 2, the initiative envisions a series of biospheres, Biosphere X, Y, and Z, capable of managing air, water, and food production. Biosphere designs. Biosphere X, a prototype for developing life support systems focused on hydroponics and aquaponics to optimize agricultural output. Biosphere Y, planned for low Earth orbit, serving as a testing ground for technologies before deploying them on Mars. Biosphere Z, a radiation-hardened biosphere intended for deep space operations, addressing the unique challenges posed by the Martian environment. Key features. Integration of closed-loop systems for recycling air and water. Advanced agricultural technologies to ensure food security utilizing both traditional and innovative farming practices. Continuous monitoring and adaptation of environmental conditions to maintain optimal living conditions. 3. Communication networks. Establishing reliable communication networks is the third phase, essential for ensuring connectivity between Martian habitats and Earth. These networks must be resilient to the Martian atmosphere and capable of handling significant data throughput for operational and research purposes. Infrastructure goals. Development of a satellite communication array to provide uninterrupted links to Earth. Implementation of redundant systems to ensure reliability in the face of Martian dust storms and other environmental challenges. Use of high-frequency communication technologies to minimize latency and enhance data transmission rates. 4. Testing and iteration. The final phase involves rigorous testing and iteration of the habitats and systems. Long-duration missions with human crews will be conducted within the biospheres to evaluate their viability. Data collected during these missions will inform iterative improvements focusing on food production metrics, resource management, and overall habitat functionality. Testing protocols. Simulated missions to assess the psychological and physiological effects of long-term habitation. Evaluation of agricultural productivity under controlled conditions. Continuous feedback loops to refine life support and habitat systems based on real-world performance metrics. Budget allocation and economic considerations. The allocated budget of $150 million poses significant challenges given the high costs associated with space missions. However, the economic implications of establishing sustainable food production in space could lead to substantial long-term savings. Current estimates indicate that food production costs in space are prohibitively high, yet developing a space farm could yield significant returns over time. Cost analysis. A 1-acre space farm could produce yields worth billions, justifying the initial investment. The costs associated with launching supplies from Earth are drastically higher than cultivating food in localized environments. Supporting the economic viability of the proposed biospheres. Common themes and divergences. A review of various sources reveals common themes regarding the necessity of developing self-sustaining ecosystems capable of operating independently from Earth. The integration of life support systems and agricultural technologies is consistently emphasized. However, divergences arise in the proposed methodologies and designs, highlighting the need for collaborative innovation and cross-disciplinary research. Timeline of events. To ensure the successful execution of the project, the following timeline outlines key milestones. 2023 to 2024, development and testing of initial designs for Biosphere X. 2025, transition to constructing Biosphere Y in low Earth orbit utilizing SpaceX's Starship for transport. 2027, initiation of life support system testing and agricultural practices in Biosphere Y. 2029, preparations for launching Biosphere Z incorporating lessons learned from prior phases. 2030, operational habitats on Mars. Facilitating human presence and exploration. Conclusion. The ambitious goal of establishing autonomous habitat systems for Mars colonization by 2030 hinges on innovative designs, economic feasibility, and rigorous testing. The interplay among robotic construction, life support, and communication systems is critical in creating a sustainable human presence on Mars. By strategically allocating resources and fostering collaborative efforts, humanity stands on the brink of a new era of exploration and habitation beyond Earth. References. 1. Space Settlement Progress. 2024, Biosphere X, Y, and Z, The Future of Farming in Space. Retrieved from spacesettlementprogress.com/spacesettlementprogress.com/category/Mars settlements/. 2. NASA. 2023, Mars Exploration Program. Retrieved from mars.nasa.gov/mars.nasa.gov/. 3. SpaceX. 2024, Starship, the next generation of space transport. Retrieved from spacex.com/www.spacex.com/. This report encapsulates the vision and strategic approach for Mars colonization through autonomous habitat systems, emphasizing the necessity of innovation and sustainability in our quest to explore and inhabit other worlds. The implementation of autonomous habitat systems for Mars colonization by 2030 involves a complex framework with counterintuitive implications, particularly regarding budget allocation, technological feasibility, and the lifecycle of biospheres. Here are some key insights. 1. Budget allocation and cost efficiency. The proposed budget of $150 million for establishing habitats on Mars is significantly lower than the estimated costs for constructing and sustaining these habitats, which could reach around $513 million for robotic construction alone. This discrepancy highlights the counterintuitive nature of funding in space exploration, where initial allocations may seem insufficient compared to the immense costs involved. The expectation that farming in space can drastically reduce food costs contradicts the historical reality of high costs associated with food production in space. While the idea is that self-sustaining ecosystems will reduce reliance on Earth, the initial investments and technological developments needed may not align with the budget constraints. 2. Robotic construction and material utilization. The reliance on advanced robotics to utilize local Martian materials for construction is counterintuitive because it assumes that such technologies will be developed and operational by the time of colonization. Historically, space missions have faced significant technological hurdles. The assumption that autonomous machines can efficiently build habitats on an alien planet raises questions about the readiness and reliability of these technologies, which may not be as advanced as anticipated. 3. Life support systems and agricultural technologies. The shift from traditional agriculture to high-tech solutions like hydroponics and aquaponics is a pivotal aspect of the life support systems phase. The counterintuitive element here is the expectation that these systems will be effective in a Martian environment where conditions differ drastically from Earth. The reliance on prototypes like Biosphere X, which has not yet been proven, raises doubts about whether the proposed agricultural systems can sustain human life. Moreover, the historical challenges faced in previous biosphere experiments indicate that replicating Earth-like conditions in space is fraught with uncertainty. 4. Communication networks and environmental resilience. Establishing communication networks that can withstand the Martian environment presents a counterintuitive challenge. The assumption that data transmission can be seamlessly maintained between Earth and Mars overlooks potential disruptions caused by the planet's unique atmospheric conditions and distance. The complexity of maintaining consistent communication networks in such an environment may lead to unforeseen complications. Contrary to the belief that technological advancements will mitigate these issues. 5. Iterative testing and real-world applicability. The final phase focuses on rigorous testing and iterative improvements based on real-world experiences within the biospheres. The counterintuitive notion is that extensive testing in simulated environments will yield results applicable to actual Martian conditions. The historical precedent, such as the Biosphere 2 experiment, shows that controlled environments often fail to replicate the unpredictability of real-world scenarios, suggesting that the iterative learning process may not yield the necessary insights for successful colonization. 6. Long-term sustainability and economic viability. The expectation that space farming can eventually yield billions in food value is counterintuitive when considering the initial costs of setup and the ongoing expenses of maintaining such systems. The concept relies heavily on optimistic projections about agricultural productivity in space, which may not materialize as anticipated. The financial sustainability of these habitats hinges on a complex interplay of technological advancements, successful agricultural yields, and the ability to maintain a closed-loop system, all of which carry inherent risks and uncertainties. 7. Human factor and societal implications. The proposal hints at the need for families, including children, to inhabit these biospheres, which raises counterintuitive issues regarding the social dynamics of living in confined artificial environments for extended periods. Historical analogs such as the challenges faced by crews in isolated environments, e.g. submarines, Antarctic research stations, indicate that psychological and social factors may pose significant challenges that are often underestimated in planning for long-duration space missions. In conclusion, while the vision for Mars colonization through autonomous habitat systems presents an exciting frontier, the counterintuitive aspects of budget allocation, technological readiness, agricultural sustainability, and human factors highlight the complexities and uncertainties of such ambitious undertakings. The report on the implementation of autonomous habitat systems for Mars colonization by 2030 presents a well-structured plan that includes 4 key phases: a budget allocation of $150 million and focuses on critical areas such as robotic construction, life support systems, and communication networks. While the report outlines essential components for achieving sustainable human presence on Mars, certain details may be overlooked that hold significant implications for the project's success. Here are some important aspects that deserve more attention. 1. Cost management and alternative funding sources. While the report mentions a $150 million budget allocation, it also acknowledges that the estimated costs for constructing habitats could exceed $513 million. This discrepancy raises questions about the feasibility of the project within the given financial constraints. Most readers might gloss over the financial implications, but understanding the funding landscape is crucial. Significance: the ability to secure additional funding or partnerships with private companies and international space agencies could determine the project's success. Cost management strategies such as utilizing local Martian resources for construction and food production could also enhance sustainability and reduce reliance on Earth-based supplies. Identifying alternative funding sources or innovative financing methods could provide the necessary support to cover the gap between budget and estimated costs. 2. Robotic construction methodologies. The first phase focuses on robotic construction using autonomous machines to build habitats on Mars. The report suggests that this approach could significantly reduce the need for heavy payloads launched from Earth. However, the specifics of the robotic technologies and methodologies remain vague. Significance: the effectiveness of robotic construction directly impacts the timeline and cost of habitat creation. Advanced robotics, AI, and 3D printing technologies are pivotal for overcoming Martian environmental challenges. Emphasizing the development and testing of these technologies can lead to more efficient construction processes, ultimately reducing costs and timeframes. The report should elaborate on potential robotic platforms, their operational capabilities, and integration with Martian geology to enhance understanding and planning. 3. Life support system innovations. The second phase highlights the importance of life support systems, drawing inspiration from experiments like Biosphere 2. However, while the report discusses various Biosphere designs, it does not delve deeply into the integration of these systems for optimal function. Significance: life support systems are critical for long-term human survival in space. Innovations in bioregenerative systems, integrated agriculture, and waste recycling could significantly enhance sustainability. Exploring synergies between different life support technologies like hydroponics and aquaponics could yield better resource management and lower costs. The report could benefit from a deeper analysis of potential life support system configurations, their interdependencies, and how they could evolve through iterative testing. 4. Communication networks and data management. Establishing reliable communication networks is emphasized in the third phase, but the report lacks specific details on the technologies to be deployed and the challenges associated with Martian communication. Significance: effective communication is crucial for coordination between habitats and Earth, especially given the time delay in transmissions. Addressing potential issues such as signal degradation due to atmospheric conditions or distance can help in designing resilient communication networks. Moreover, data management strategies to handle the vast amount of information generated by habitats, e.g., environmental data, health metrics, should be considered. Focusing on both hardware and software aspects, including cybersecurity and data transmission protocols, can enhance operational efficiency and safety. 5. Human factors and psychological considerations. The final phase involves testing habitats with human crews, but the report does not address the psychological and social dynamics of living in isolated environments for extended periods. Significance: human factors play a critical role in the success of long-duration missions. Addressing psychological well-being, social interactions, and conflict resolution strategies is essential for maintaining morale and productivity. The report could benefit from incorporating studies on group dynamics, mental health support systems, and recreational activities to ensure that the habitats are not only physically sustainable but also psychologically conducive for human habitation. 6. Iterative testing and real-world feedback. The report mentions rigorous testing of habitats and systems, but there is limited discussion on the iterative feedback loop from these tests to influence design and operational strategies. Significance: iterative testing is vital for refining technologies and systems based on real-world performance. Establishing a feedback mechanism that allows for continuous learning and adaptation can lead to improved designs and operational efficiencies. The report should emphasize the importance of documenting lessons learned from each testing phase and how these insights will be integrated into future iterations of biospheres and habitats. 7. Collaborative ecosystems and partnerships. While the report outlines the phases of habitat development, it does not address the potential for collaboration with other organizations, governments, or private entities. Significance: the complexity and scale of Mars colonization necessitate a collaborative approach. Engaging with international space agencies, universities, and private companies could diversify expertise and resource availability. Potential partnerships can also lead to shared technologies, funding opportunities, and innovative solutions to common challenges. The report should explore the landscape of potential collaborators and the benefits of fostering a collaborative ecosystem for Mars colonization. Conclusion: the implementation of autonomous habitat systems for Mars colonization presents a groundbreaking opportunity for humanity. However, to ensure success by 2030, it is imperative to address the overlooked aspects identified above. By focusing on cost management, technological specifics, life support innovations, effective communication, human factors, iterative testing, and collaborative ecosystems, the project can maximize its chances of establishing a sustainable human presence on Mars. These elements not only enhance the robustness of the proposed plan but also ensure that it is adaptable to the unique challenges of space exploration. 1. Robotic construction and cost efficiency. The first phase of the implementation involves advanced robotics systems for habitat construction on Mars, utilizing local materials to minimize payloads from Earth. The projected cost of constructing habitats is around $513 million, which is significant compared to the allocated budget of $150 million. This highlights the need for innovative and cost-effective solutions that can leverage automation and local resources, potentially setting the stage for future construction methodologies not only on Mars but in other extraterrestrial environments. 2. Life support systems and sustainable ecosystems. The second phase focuses on developing life support systems inspired by previous Biosphere experiments. The integration of hydroponics and aquaponics in Biosphere's X, Y, and Z aims to create self-sustaining ecosystems that can produce food, manage waste, and recycle water effectively. This point is critical for ensuring long-term human habitation on Mars, as it addresses the challenge of food security and resource management in a hostile environment. The establishment of these ecosystems could serve as a blueprint for future space colonization efforts. 3. Communication networks and operational coordination. Establishing robust communication networks is crucial for facilitating real-time coordination between Mars habitats and Earth. This phase emphasizes the need for resilient systems capable of handling large volumes of data and ensuring seamless communication despite the challenging Martian environment. The success of these networks will be vital for operational efficiency, research collaboration, and maintaining a connection with Earth, which is essential for the psychological and operational well-being of Mars colonists. 4. Testing, iteration, and human factors. The final phase involves extensive testing of the habitats and life support systems through long-duration missions with human crews. This iterative process is designed to gather real-world data on the viability of the systems, prompting adjustments based on performance metrics like food production and resource management. Understanding human factors such as crew dynamics and psychological resilience during prolonged isolation will be critical for the success of Mars colonization. This focus on human-centered design and testing will inform future missions and help address the complexities of human life in space. Here are 3 famous historical cases that share similarities with the theme of implementing autonomous habitat systems for Mars colonization, particularly in terms of innovative engineering, sustainability, and exploration. 1. The Apollo Moon Landing, 1969. The Apollo program, particularly Apollo 11, marked a monumental achievement in human space exploration. NASA's mission to land humans on the Moon involved intricate planning, engineering, and execution similar to the proposed phases of Mars colonization. The program used advanced technology for its time, including the lunar module that autonomously landed on the Moon's surface. The mission required extensive life support systems to ensure astronaut safety, similar to the life support systems planned for Martian habitats. Apollo's success laid the groundwork for future space exploration, demonstrating the feasibility of human habitation in extraterrestrial environments. 2. Biosphere 2 1991 to 1993. Biosphere 2 was an ambitious project aimed at creating a self-sustaining ecological system to study the interactions within a closed environment. Located in Arizona, it housed a variety of ecosystems including a rainforest and an ocean, and was designed to explore the viability of sustaining human life in isolated environments. The project faced numerous challenges, including issues with oxygen levels and food production, ultimately providing critical data on closed system life support and resource management. The lessons learned from Biosphere 2 are directly relevant to the proposed life support systems for Mars habitats, as they highlight the complexities of creating sustainable ecosystems outside of Earth. 3. The International Space Station ISS launched in 1998. The ISS represents a collaborative effort among multiple countries to maintain a permanent human presence in low Earth orbit. It serves as a living laboratory where astronauts conduct scientific research and test life support systems in microgravity. The ISS has provided valuable insights into the long-term effects of space habitation on the human body, as well as the effectiveness of various agricultural practices in space. Its modular design and reliance on international cooperation echo the proposed communication networks and testing phases for Mars habitats, emphasizing the need for robust, interconnected systems to support human life in space. These historical cases illustrate the progression of human exploration and the technological innovations that have been pivotal in overcoming challenges related to habitat construction and sustainability in extraterrestrial environments. Future outlook: autonomous habitat systems for Mars colonization by 2030. As we approach the target year of 2030, the vision for Mars colonization through autonomous habitat systems is becoming increasingly tangible. The successful implementation of these systems is anticipated to unfold in 4 key phases, each critical to establishing a sustainable human presence on Mars. Here is a detailed look at these phases, their implications, and the broader future outlook. 1. Robotic construction. Timeline: 2023 to 2025. The first phase focuses on robotic construction, leveraging advanced autonomous technologies to build habitats using local Martian materials. By 2025, we expect to see prototypes and initial infrastructure laid out primarily using materials like regolith. The funding constraint of $150 million will necessitate innovative, efficient approaches, possibly including 3D printing technologies that utilize Martian soil. Future predictions: cost reduction. As robotic technologies mature, construction costs could decrease significantly, paving the way for larger-scale projects. Enhanced robotics. Improvements in AI and robotics will enable more complex tasks, reducing reliance on Earth-based resources and expertise. Increased safety. Automated systems will minimize human risk during construction, setting a precedent for future extraterrestrial building projects. 2. Life support systems. Timeline: 2025 to 2029. The second phase will see the creation of life support systems to manage vital resources like air, water, and food. Drawing from concepts like Biosphere 2, the design of Biospheres X, Y, and Z will evolve, focusing on sustainable agricultural practices such as hydroponics and aquaponics. Future predictions: agricultural innovation. The development of efficient food production systems will make long-term habitation feasible, driving population growth on Mars. Closed-loop systems. Advances in bioregenerative life support systems will enable complete recycling of essential resources, minimizing the need for resupply missions from Earth. Health and safety. Enhanced environmental controls will ensure the health and safety of inhabitants, addressing challenges posed by the Martian environment. 3. Communication networks. Timeline: 2026 to 2030. Establishing robust communication networks will be critical for coordination between habitats and Earth. Reliable systems will facilitate data transfer and resource management, ensuring that operations run smoothly. Future predictions: interplanetary internet. By 2030, we may see the establishment of an interplanetary internet significantly improving communication latency issues. Increased collaboration. Enhanced communication will foster collaboration between Mars and Earth-based teams supporting research and operational efficiency. Emergency response. Advanced communication systems will enable rapid response capabilities in emergencies. Crucial for the safety of Mars inhabitants. 4. Testing and iteration. Timeline, 2028 to 2030. The final phase will involve rigorous testing of habitats and systems with long-duration missions simulating Mars conditions. This phase will highlight the importance of iterative improvements based on real-world feedback. Future predictions. Human trials. By 2030, we anticipate the first human crews living in Mars habitats, providing invaluable data for system optimization. Continuous improvement. Lessons learned will drive the design of future habitats, ensuring that subsequent missions are more efficient and effective. Scaling up. Successful testing will lead to plans for larger habitats and more complex infrastructures accommodating larger populations. Economic considerations and sustainability. The projected budget of $150 million poses challenges but also opportunities for innovative financing and cost management. The high costs of food production in space highlight the necessity of developing efficient agricultural practices. As the technology matures, we can anticipate cost-effective farming. Space farming could drastically reduce reliance on Earth-supplied food, with estimates suggesting significant returns on investment over time. Economic viability. The establishment of a self-sustaining economy on Mars will be crucial, with potential for trade and export of Martian resources. Investment opportunities. As public and private interest in space exploration grows, we may see increased investment in technologies relevant to Mars colonization, further driving innovation. Long-term vision. The successful implementation of autonomous habitat systems on Mars will set a precedent for future extraterrestrial colonization efforts. By 2030, we can expect human presence on Mars. A sustainable human settlement will not only serve as a scientific outpost but also as a stepping stone for deeper space exploration, potentially targeting destinations like the Moon and beyond. Space as a new frontier. The challenges overcome in establishing a Martian colony will drive advancements in technology, making space more accessible for future generations. A new era of exploration. The success of Mars colonization efforts could lead to the establishment of a new era in human exploration, with aspirations for multiplanetary living becoming a reality. In conclusion, the roadmap laid out for autonomous habitat systems by 2030 indicates a transformative period for human space exploration. With innovations in robotics, life support, and communication, the dream of living on Mars is set to become a reality, paving the way for humanity's expansion into the solar system.